Mars is up there, and we have rockets, powerful ones. So why don't we just point one at it and go? I mean, really, why not? You can see Mars with the naked eye at a clear night. It's right there. The idea doesn't seem that complicated. And yet every single Mars mission in history has taken between 6 and 9 months to arrive. Every single one has launched during a specific window, and every single one has traveled in a giant curve through space, going almost sideways relative to Mars before swinging into mid-it. Nobody aimed at Mars. Nobody just went. And the reason why is one of the most counterintuitive and beautiful things in all of physics. Hello, my name is Lilith, and today let's point the rocket to Mars and go. Let's start at the beginning. You want to leave Earth. Earth's gravity is pulling everything on its surface downward. To leave, you don't just need to go up. Like, this is not enough. You need to go fast that you never come back down. That speed has a name: escape velocity. For Earth, it's 11.2 kilometers per second. To put that in perspective, a commercial plane cruises at 0.25 kilometers per second. A bullet travels half a kilometer per second. Escape velocity is more than 20 times faster than a bullet. Not for a moment, sustained, the entire way up, just to break free. And here's the thing. The moment you achieve escape velocity, the moment you leave Earth, that's just the beginning. You have just escaped one gravitational trap and are now sitting inside a much larger one, the Sun. Everything in a solar system, every planet, every moon, every comet is in orbit around the Sun, including Earth. When a rocket launches from Earth, it inherits that velocity. It is not floating still in space, it is already moving around the Sun along with the planet it just left at a speed of 30 kilometers per second. And Mars isn't standing still either. It is also moving around the Sun at about 24 kilometers per second. So you don't have a stationary target. You have a moving one, hundreds of millions of kilometers away. One that will be in a completely different position by the time you arrive, and no matter how fast you go. This is why nobody just points a rocket at Mars. It isn't where you're aiming. Mars is where you're predicting. In 1925, a German engineer named Walter Hohmann published a small book about space travel. He had never built a rocket. He had never been to space. Nobody had. But he sat down and worked through the mathematics of orbital mechanics. And his conclusion is still used in space exploration. So the most fuel-efficient path between two planets is not a straight line. It's not even close to a straight line. It's an ellipse. And here's the way it works. Everything in a solar system is already orbiting the Sun. Your spacecraft is in orbit, Earth's orbit. Mars is in its own orbit, farther out, moving more slowly. To get from one orbit to the other, you don't aim at Mars. You change which orbit you're in. You fire your engine once, just once, to stretch your circular orbit into an ellipse. Its inner edge touches Earth's orbit. Its outer edge reaches all the way out to Mars's orbit. Then you turn the engine off. For about 9 months, you drift along this elliptical path, falling outward through the solar system with no propulsion at all. The Sun's gravity keeps you curving in the right direction, and if the timing was calculated correctly, you reach the outer edge of your ellipse at exactly the moment Mars arrives at the same point. Mars doesn't wait for you, you intercept it. Then you fire your engine one more time, and this time in the opposite direction, to slow down and let Mars's gravity capture you. 2 engine burns, that's it. One to leave Earth's orbit, one to enter Mars's orbit. Everything in between is free, carried by orbital mechanics and the geometry of the solar system. This is called the Hohmann transfer orbit. And it is the reason every Mars mission takes roughly 9 months. Not because we can't go faster, because the path uses the least fuel, and the fuel amount is a problem. Russian scientist Konstantin Tsiolkovsky proved in 1903 that the more speed you want, the exponentially more fuel you need to carry. And the fuel itself has to be accelerated, which needs more fuel, which needs more fuel, and so on. This is called Tsiolkovsky's rocket equation, or as astronauts call it, the tyranny of the rocket equation. Essentially, you run out of rocket before you run out of ambition, and it compounds when you consider the physical structure. The square cube law states that as a rocket scales up, its volume and therefore its mass grows much faster than its surface area. Actually, we have a video about the most cruel law. It's here. Here, check it out. So a rocket twice the size isn't twice as heavy, it's far heavier, which means you need even more fuel, which means it gets even heavier. The equation doesn't get easier when you make things bigger, it gets worse. In conclusion, going faster isn't expensive. With the chemical rockets we use today, it's eventually just impossible. And the Hohmann transfer orbit is the most fuel-efficient trajectory to Mars, with a journey of approximately 8 to 9 months. However, there is another catch. Earth and Mars only align in the correct geometry for a Hohmann transfer once every 26 months, known as a launch window. Just several weeks. Miss it and you're waiting over 2 years for the next opportunity. These limitations run both ways. After arriving at Mars, the return window takes another 18 months to open. Any crewed Mars mission isn't just a trip, it's a commitment to stay until the solar system says you can leave. And if something goes wrong after just 30 days into the mission, the earliest possible return to Earth is around day 392. Meaning you're still over a year away from home. Abort at Mars arrival and you're looking at roughly 2 years from departure before you're back, which is exactly why the launch window, the trajectory, and every calculation have to be perfect before you leave the ground. I hope that at this point you are as fascinated as I am with the idea that Hohmann came up with this method long before humanity actually used it in space. Now it's time for another extraordinary idea that was born at the beginning of the 20th century. What if you don't have enough fuel to reach your destination at all? What if the Hohmann transfer, already the most efficient path, still requires more energy than your rocket can provide? Friedrich Zander, the great mind behind the first ever liquid-fueled rocket, in 1925 proposed an idea to steal speed from a planet. This is called a gravity assist, or gravitational slingshot. When a spacecraft swings behind a planet, the planet's gravity grabs it and flings it forward, adding the planet's own orbital velocity to the spacecraft's speed. It arrives at one speed and leaves at another. The very first time humanity put this idea to use was with the Soviet probe Luna 3. This time it wasn't about gaining speed, but about changing its orbit so the probe could photograph the far side of the moon. NASA's Mariner 10, launched in 1973, became the first mission to use a genuine interplanetary gravity assist, swinging past Venus to redirect its path toward Mercury. And the most remarkable demonstration came from Pioneer 10, which used Jupiter's gravity to reach escape velocity and become the first human-made object to leave the solar system entirely, crossing the boundary in 1983 with a speed of 132,000 km per hour, or around 36.7 km per second. Voyager 1, the furthest human-made object from Earth. Right now, in April 2026, it is almost 173 astronomical units away, 1 astronomical unit being the distance between the Earth and the Sun. It reached interstellar space not by carrying enormous amount of fuel, but by swinging past Jupiter and gaining 10 km per second, then past Saturn and gaining another 5, enough to reach 17 km per second and never stop. In August 2012, it crossed the boundary of the solar system entirely. This November, it will be exactly 1 light day away from us, meaning even a radio signal will need 24 hours just to reach it. Engineers who designed these trajectories were not just solving a problem, they were reading the solar system like a map, finding the currents, the slopes, the places where you could fall in a useful direction and emerge somewhere better. And keep in mind, the people who calculated this didn't have supercomputers. In many cases, they didn't have computers at all, just mathematicians, pencils, and time. There's one more thing I want to talk about, something that doesn't get mentioned enough. The Sun is the largest gravitational body and the stationary center of our solar system. It contains 99.8% of all the mass in the solar system, and that mass creates an enormous gravitational pull. Here is a fact that surprises almost everyone. It is actually harder to hit the Sun than to escape the solar system. Think about that. To send a spacecraft directly into the Sun, first you need to cancel Earth's orbital velocity, 30 km per second, which is the speed Earth orbits the Sun. If you can manage it, the spacecraft stops moving sideways and just falls straight to the Sun. And that kind of speed can be achieved only with gravity assist or using enormous amounts of fuel. With our current technology, it is very, very expensive and requires more fuel than any rocket we have ever built. And that's why leaving the solar system entirely is easier. Because launching from Earth, you already inherit those 30 km per second. You only need an extra 12 on top of that to escape the Sun's gravity forever. This is why there has never been a mission designed to fly directly into the Sun. The Parker Solar Probe, launched in 2018, is the closest we have come. But even that uses gravity assist from Venus to slowly bleed off orbital velocity over multiple years, spiraling gradually inward rather than going directly. The Sun's gravity holds everything together, but it also makes everything harder to reach. No space mission is just about escaping Earth's gravity. It is navigating inside the Sun's gravity well, using the orbital momentum of planets as stepping stones, borrowing velocity where it can, spending it carefully where it must. So why can't we just point a rocket at Mars? Because Mars is moving, because we are moving. The path requires both planets to be in exact the right alignment at the exact right moment. Space travel is like predicting where a moving target will be months from now, and then throwing something at the future position with such precision and calculation that it arrives at the right moment and the right speed. And the extraordinary thing is, we can do it. We have done it dozens of times. There is something beautiful about the fact that the most efficient way to travel through the solar system is not to fight the forces around you, but to read them, to understand them. Every trajectory ever calculated, every gravity assist ever executed, every launch window ever waited for, they're all conversations with physics. And physics, it turns out, is a very patient teacher. Thank you for your time. See you in the next video.